The vast emptiness of the universe hides countless unsolved mysteries and riddles. In the deepest darkness of outer space, there lurk many striking objects with unusual and sometimes even anomalous properties. Despite all the research, we have learnt only a very small part of the incredible diversity of the universe. And today, we're going to take a plunge into its most mysterious depths. Our virtual journey will begin alongside the legendary Voyagers, which have been traveling through the expanses of space for decades now. After whizzing through the icy darkness of interstellar space, we will visit several of our nearest stars, including the amazing Alpha Centauri. And after that, we will dive into the uncharted depths of the Milky Way to find rogue planets hidden in the darkness. Leaving millions of light years of space behind, we will finally reach the majestic Andromeda Galaxy, which has been attracting astronomers' attention for hundreds of years. As we continue on this fantastic journey, we will eventually reach the largest empty areas in the universe, voids which insatiably absorb even relic radiation. They are the inextinguishable eternal echo of the Big Bang. Let's get ready, and we begin. On the 15th of April 2021, the automatic space probe New Horizons became the fifth spacecraft in the history of the humanity to go beyond the point of 50 astronomical units from the Sun. It was the Voyagers that had crossed this mark before, with the probes Pioneer 10 and Pioneer 11 the first ever to do so. None of these space wanderers are likely to ever return to the Earth. With some of them still active on their missions, others have gone quiet forever. Spacecraft New Horizons. Start of mission 19th of January 2006. Distance to Earth 52 astronomical units. Speed 14 km per second or 3 astronomical units per year. Main goal Pluto and Charon. Mission status successfully completed. Condition operational. Just like most other interplanetary space probes, New Horizons performed a gravity assist maneuver near Jupiter before setting out to its target. Not only did it greatly boost the spacecraft's speed, but also allowed it to capture high-quality images of the largest planet in the solar system alongside its satellites. Besides, the probe's cameras captured the first video ever of an erupting volcano on the surface of Jupiter's satellite Io. After the gravity boost had been completed, the probe made for the main target, Pluto. The spacecraft reached the planetoid's environs in January 2015. The mission's main goal was to explore Pluto and Charon from different perspectives that involved taking photos of and mapping these remote space object surfaces. In addition, the probe estimated the magnetic field's values and the solar wind activity close to the objects, and collected information about their atmospheres and surface reflection properties. It goes without saying that the program also involved search for Pluto's as yet undetected satellites and more accurate measurements of Pluto's orbit's parameters. Having completed the main mission, the probe continued to be useful. It flew beyond Pluto's orbit and went on to explore objects in the Kuiper Belt. That is how images of Quaoar, R1 and Arakoth were produced. Thanks to the probe's cameras, the distances to the stars Proxima Centauri and Wolf 359 were measured. Unfortunately, the radioisotope generator on board the spacecraft is expected to start running low from 2026, and eventually all the meters will switch off one after another. New Horizons will continue on its way beyond the boundaries of the solar system, and by the year 2038, the distance between the probe and the Sun will have grown to be 100 astronomical units. By that time, the energy generator on board the spacecraft will have stopped operating completely, and it will be impossible to get any connection with it. Following a hyperbolic orbit, New Horizons will exit our system, never to come back. The same thing happened with two other probes, Pioneer 10 and Pioneer 11. They hit an escape trajectory from the solar system a while ago. In fact, they were the first automatic space probes ever to be sent into interstellar space by humans. Spacecraft Pioneer 10. Start of mission 3rd of March 1972. Distance to Earth 127 astronomical units. Speed approximately 12 km per second or 2.5 astronomical units per year. Main goal Jupiter. Mission status successfully completed. Condition not operational. The spacecraft reached Jupiter's system on the 4th of December 1973 after completing a 641-day journey through space. During the mission, images of the gas giant's surface and its largest satellites were beamed back to the Earth, and the planet's atmospheric composition and magnetic field were gauged. In addition, Jupiter was found to emit 2.5 times more thermal energy than it receives from the Sun. The data, unique at the time, became the basis for understanding the makeup of gas giants and their satellites. The trajectory of the second probe, Pioneer 11, through space passed Jupiter too, but its main target was the other gas giant of our system, Saturn. The probe's scientific instruments gauged the planet's magnetic field, and the cameras on board took quite a few snapshots not only of the gas giant itself and its system of rings, but also two of its satellites, Titan and Mimas. According to the estimates, the current distance between Pioneer 11 and the center of our system is around 106 astronomical units. On completing their main mission, both probes continued on their way, moving further and further away from the Sun. Unfortunately, both of them are out of range now, with the last signal from Pioneer 10 received back in 2003. The last signal from Pioneer 11 was received in 1995. Supposedly, both of them are now rapidly moving beyond the boundaries of the solar system. Incidentally, having no chance of ever catching up with either of the two probes we're going to talk about next, the Pioneers were launched at a much earlier date. Spacecraft Voyager 1. Start of mission 5th of September 1977. Distance to Earth 154 astronomical units. Speed around 17 km per second or 3.6 astronomical units per year. Main goal Jupiter and Saturn. Mission status successfully completed. Condition not fully operational. The contribution of Voyager 1 to the solar system's exploration can hardly be overestimated. It is thanks to this probe that several new Jupiter satellites were discovered, alongside its ring system, which was big news. The Voyager's cameras captured volcano eruptions on Io and provided hard evidence that Jupiter's Great Red Spot is an enormous storm. The probe beamed back hundreds of photos of the largest planet of our solar system and its satellites. After the spacecraft crossed Neptune's orbit, the meters on board sent back a great amount of valuable data about interstellar plasma. Voyager 1 left both the Kuiper Belt and the heliopause behind a long while ago, and is now rapidly crossing the area of the solar system's scattered disk, making for the inner boundary of the hypothetical Oort cloud. It is not only the remotest man-made object in space, but also the fastest of all the spacecraft on their way to exit our system. Being the first space probe to have traveled that far from the center of the solar system, Voyager 1 offered scientists a unique opportunity to study the heliopause. This is the area around our Sun where solar wind pressure and interstellar gas pressure balance. When the charged particles emitted by the star collide with rarefied plasma, elaborate structures form out of elementary particles and magnetic fields. Studying them is crucial for understanding processes taking place in the universe. Unfortunately, by around the year 2025, the power of the radioisotope thermoelectric generators on board the probe will have run out completely, and the connection will have been lost. In 300 years, Voyager 1 is estimated to reach the inner boundary of the hypothetical Oort cloud. It will take the spacecraft approximately 30,000 years to go clean through, and after that it will fly beyond the boundaries of the solar system. 10,000 years later still, the probe will fly by the star Gliese 445 at a distance of 1.6 light-years, and then it will eventually get lost in the infinite depths of outer space. Speaking about Voyager 1, we can't but mention its twin, launched from the Earth on the 20th of August 1977. Voyager 2 had Saturn, Uranus and Neptune for its targets, but it also approached Jupiter for a gravity boost. It's the images taken by this probe that allowed scientists to assume that there are subsurface oceans on Ganymede and Europa. On reaching Saturn, Voyager 2 gauged the gas giant's temperature and magnetic field and discovered several new satellites. It goes without saying that lots of snapshots were taken of both Saturn's surface and its rings. Next in line on the probe's way were Uranus and Neptune. The flyby yielded a great number of unique snapshots, and in total 17 of the two planets' satellites were discovered. Also, it was found that both Uranus and Neptune have ring systems. Under Neptune's gravitational influence, the spacecraft changed its trajectory and left the ecliptic plane. This meant that Voyager 2 wouldn't be able to approach the other objects in the solar system, but it still had other exciting things to look forward to. Thus, the probe was to collect invaluable data about interstellar plasma and cosmic wind, as well as to measure distances to stars and explore the heliosphere. The probe is currently as far as 128 astronomical units away from the center of our system, with the distance growing by 15.37 kilometers every second. It's going to take it around 42,000 years to approach Ross 248, a dim red dwarf in the constellation Andromeda. The minimal distance between Voyager 2 and the star will be about 1.7 light-years, and around 300,000 years since its launch, chances are it will fly by Sirius at a distance of 4.3 light-years. Unfortunately, it is impossible to distinguish such a tiny object from the Earth that far away. It's hardly a secret that distances in the universe are mind-boggling. Even with the best modern engines, a journey to the Moon is going to take several weeks, and more than 6 months to reach Mars by the most optimal trajectory. If we think about the legendary Voyagers, after 45 years of traveling through space, they managed to leave only the inner part of the solar system. They are destined to spend several of the next millennia drifting through the scattered disk and the hypothetical Oort cloud. The fastest spacecraft at the moment is the Parker Solar Probe, whose speed in 2025 will reach a record-breaking 194 kilometers per second. However, this will happen only due to the Sun's gravity, which will never allow it to leave the environs of our star, and so the probe is doomed to soon burn up in its photosphere. Apparently, chemical jet engines, which are currently so widespread, have exhausted their development potential and are hardly suitable for interstellar travel. Of course, there are various alternative concepts, such as nuclear pulse propulsion or solar sails, but implementation of either of these is hampered by a number of serious issues. It is highly likely that sooner or later, most of these difficulties will be overcome. Another important task crucial for long-distance travel should be taken into account, namely the creation of a stable and powerful source of energy. All modern spacecraft are relatively small in size and are equipped with reliable but low-power power sources. For example, autonomous research probes are usually powered by isotope batteries, which inevitably degrade over time. If we revisit the legendary Voyagers, it turns out that almost all of their systems have long since been de-energized, and the spacecraft themselves have been moving by inertia for many years. The ISS and other orbiting space stations combine solar panels and radioisotope thermal generators, but most of their power is consumed by life support systems, and the ion drives serve only to adjust the orbit. In the case of an extended manned mission to a remote planet or star, however, a spacecraft would need much more power. Meanwhile, 99% of the way to another star inevitably passes through interstellar space, devoid of obvious energy sources. Even radiation of the brightest stars is noticeably weaker here and dissipates in the vast expanses of space. Therefore, to travel to other worlds, we need an autonomous, powerful, and preferably inexhaustible source of energy. To figure out a potential way of solving this problem, we have to take a closer look at the universe's structure. It is there that a number of amazing physical processes can be observed, which might prove to contain a key to stars' secrets. To do this, we have to take a slight detour. In 2017, a collaborative effort of scientists from Princeton and Hong Kong yielded an incredible device that at first glance violates the fundamental laws of physics. A microscopic mechanism consisting of two toothed silicon plates spaced 100 nanometers apart was able to generate a small amount of energy, literally, from nothing. It would seem that such a phenomenon should grossly violate the law of conservation of energy, one of the fundamental principles of the universe's makeup. However, in fact, it is not as simple as that. The amazing device is based on the Casimir-Polder effect, discovered back in the middle of last century. Putting it simply, it boils down to this. If two thin plates are placed in a vacuum a very small distance apart, they will begin to be mutually attracted. The phenomenon is closely related to the Heisenberg's uncertainty principle, from which follows the existence of the so-called zero-point vacuum fluctuations. They are pairs of virtual particles that constantly appear at any point of the universe, by and large out of nowhere. However, their lifetime is only 10 to the power of minus 24 seconds, after which the particles disappear back into nothingness and the global balance is restored. At the same time, if virtual particles with any parameters are generated in open space, only those that have strictly defined wavelengths can be generated between the plates. Consequently, more numerous external particles press on the plates harder than internal ones. Just to illustrate, one can imagine that the space between the plates has a negative pressure. It's as if a little more substance were pumped out of the vacuum. The resulting mechanical tension can be transformed into an electric current, which is exactly what the Princeton and Hong Kong researchers did. And although the current was quite weak, it's the principle itself that matters. Because this way, our world receives energy virtually from nothing. Even a low-power source of inexhaustible energy is of enormous practical value. For example, as an autonomous power supply for microprocessors and other high-precision equipment. For example, the Voyagers equipped with such a hypothetical battery could still transmit data from their instruments to Earth. This opens up promising vistas for exploring deep space. Many interesting physical phenomena follow from the Casimir effect, one of which is the so-called Scharnhorst effect. According to calculations, the speed of light in the space between the plates should exceed the standard value of 300,000 km per second because there are no collisions of photons with virtual particles. Although modern technology does not yet allow this experiment to be carried out, its mathematical justification leads to far-reaching conclusions. For example, the widely known project of the hypothetical superluminal engine known as Alcubierre's bubble was proven to be potentially feasible by scientists from Baylor University, Gerald Cleaver and Richard Debussy. They combined the equations of quantum field theory and the general theory of relativity, producing a complex but clear rationale for a bold concept. It is worth mentioning that according to quantum field theory, space has not 3 dimensions but many more. But this becomes noticeable only at the level of the microcosm. Applying the equations of this theory to calculate the Casimir effect, the researchers came to the conclusion that it is possible to control its properties with the help of a powerful energy impact. If we condense the space behind the hypothetical starship and make it more rarefied in front, then there appears an area similar to the Alcubierre bubble, which is capable of moving at superluminal speeds. The laws of relativity are not violated here, because it is not the ship itself that is moving, but the space around it. On the other hand, From the very beginning, the main problem of creating such a bubble was considered to be the incredible amount of energy required. According to some calculations, an entire planet must be converted into radiation to form a sphere capable of accommodating a starship. If researchers manage to scale generators based on the Casimir effect to the required capacity, we will be able to obtain energy anywhere in the universe, literally from nothing. Of course, there are still many problems to address for a starship to be fully operational, because outer space is not the most friendly environment for humans. For example, it is permeated with deadly radiation, which not only destroys cells of living organisms, but also causes negative mutations in their offspring. Thick metal shields or magnetic fields with certain parameters may be used as protection against it, and both of these approaches have their advantages and disadvantages. Another potential threat could be accidental collisions with micrometeorites and cosmic dust. At high velocities, even a tiny grain of sand has incredible kinetic energy and can pierce through a metal plate. It goes without saying that on a long interstellar flight, repair options are extremely limited, and a hole in the hull may prove to be fatal. In addition, a long expedition without support from Earth requires creating a closed biosphere within the starship. Scientists from different countries are currently working on this. For example, various plants have been grown on board the ISS for quite a number of years, both for scientific purposes and for consumption. In addition to that, engineers are developing systems for recycling waste, including biological waste products. However, a fully fledged orbital ecosystem is still a long way off. The Earth has been emitting structured radio signals into space for around 100 years now. The radio noise from the Earth reached dozens of other stellar systems long ago, including Arcturus, lying 37 light-years away from us, and Aldebaran, which is roughly 65 light-years away. Besides, our radio signals may be heard on the surfaces of a great number of potentially habitable exoplanets, like Ross 128b or Gliese 667cc. Still, the triple stellar system of Alpha Centauri remains the closest neighbor of the Sun, which automatically makes it the first obvious candidate for the destination of the first ever interstellar flight. Alpha Centauri is known to be a multiple stellar system made up of 3 components. 2 of the larger ones are relatively close to each other. Seen with the naked eye, they appear to be a single source of light. The 2 components follow a slightly elongated orbit around the common mass center, which takes around 80 years to complete. The maximal distance between the stars may reach 35 astronomical units, with the minimal distance reaching 11.2 astronomical units. As for the distance between these objects and the Sun, it is reportedly 4.36 light-years. The most massive, the largest and the brightest component in the system is dubbed Alpha Centauri A. This is a main sequence star with a mass of about 108% that of the Sun. Its radius is reportedly 1.22 times that of our Sun. Even though the surface temperature and the spectral class of Alpha Centauri A are close to those of our star, it emits 1.5 times as much energy. There are no confirmed exoplanets in the environs of this star. However, while the star was being observed in the infrared in 2021, some evidence was found of there being a planet-like object close by. According to preliminary estimates, its mass may be anything from 9 to 35 Earth masses, and its radius may measure 3.3 to 7 times that of our planet. 1.1 astronomical units away from its parent star, the hypothetical celestial body completes a full orbit around it within roughly a year. Additional observations are called for to verify the data, which can be done with the help of either the James Webb telescope or else Earth-based observatories. The second component of the system is called Alpha Centauri b, or Ptolemy, and it also falls into the class of main sequence stars. However, its mass is 10% less than that of the Sun, and its radius measures only 86% or so that of the Sun. Ptolemy is also slightly cooler than our star, Its surface temperature is reportedly 5,260 Kelvin, or slightly lower than 5,000 degrees Celsius. With these factors combined, the celestial object has an orange hue and its luminosity is on average twice as low as that of our Sun. Incidentally, Alpha Centauri b emits a lot more energy in the X-ray range compared with other objects of its class. Besides, the star is peculiar for its temper, and there are bright flares and ejections to be seen on its surface. No confirmed exoplanets have been detected near this star either. In 2012, a group of astronomers from the Geneva Observatory put forward a suggestion that there was a planet very close to it, whose orbital period was around 12 days and whose radius measured slightly less than that of the Earth. The suggestion was made based on 4 years of observation of the star's proper motion. However, 3 years later, a mathematical error was detected to have been made in the course of data processing, and so the idea of there being a planet was found to be erroneous. The third component of the system is a stark contrast to the first two. It is a red dwarf with a mass approximately 12% that of the Sun. Its size is about 7 times smaller than that of the Sun. Its surface temperature is only slightly higher than 3000 Kelvin, and its luminosity is just a measly 0.17% that of the Sun. Of all the components of the Alpha Centauri system, it is this dim space object that is the closest one to the Sun, lying 4.25 light-years away from it. This is what earned it its name, Proxima Centauri, which is Latin for closest. Besides, the object is getting nearer and nearer. Thus, in 26,700 years, it will be only a bit more than 3 light-years away. Still, this star cannot be seen from the Earth on account of its low luminosity. Proxima is noticeably far from its two companions in the stellar system. This distance is currently around 13,000 astronomical units or 0.21 light-years, but in the next 300,000 years it is expected to gradually shrink to just 4,100 astronomical units. It takes Proxima 547,000 years to orbit around the system's common mass center. Unlike its two larger neighbors, the Proxima Centauri system boasts 2 confirmed exoplanets, as well as at least one hypothetical object. Besides, studies of the star in the infrared allowed scientists to assume that there is a dust ring and probably a great number of small celestial objects, like asteroids or comets. The first planet in the system, Proxima Centauri b, was detected in 2016 by the radial velocities method. 4 years later, in 2020, it was confirmed by spectrographic studies with the help of the largest Earth-based telescope on our planet, VLT, the Very Large Telescope. According to the updates, the exoplanet lies 0.05 astronomical units away from its parent star, and it takes it roughly 11 Earth days to complete a full orbit. Estimates show that the planet's mass is 10 to 20% bigger than that of the Earth, and its radius measures about 1.3 times that of our planet. Mathematical modeling revealed that Proxima Centauri b gets about 1.5 times as little thermal energy from its star as does the Earth from the Sun. Its average temperature is 234 Kelvin, or 39 degrees Celsius below zero, which means that hypothetically there could be liquid water in some areas on the planet. As the celestial body is extremely close to its host star, however, it is likely to be tidally locked, so it faces the star with one and the same side. A dense atmosphere could compensate for sharp contrasts in temperatures, which are inevitable in such conditions, but just like any other red dwarfs, Proxima Centauri is often seen to eject stellar matter. Also, ionizing radiation flares are observed. It is assumed that such activity gradually destroys the atmosphere of the closest objects. A powerful magnetic field that could be encompassing Proxima Centauri b could offer some protection against the destructive process, but chances that there is any magnetic field there are thin. In the year 2020, another planet was confirmed to exist in the system. A space object dubbed Proxima Centauri c lies roughly 1.5 astronomical units away from the center of the system. Its orbital cycle is slightly over 5 years. As for the object's mass, it may be 6 to 8 times that of the Earth, but its radius hasn't been estimated at the time this video is posted. Depending on its size, meanwhile, the exoplanet will fall either in the category of mini-Neptunes or super-Earths. As Proxima Centauri c lies quite a big distance away from its parent star, its temperature is remarkably low, about 39 Kelvin or 234 degrees Celsius below zero. According to some observations, the planet may have a ring system whose radius is roughly 5 times that of Jupiter. Also, based on the latest data from VLT, a remarkably small exoplanet is expected to lie 0.029 astronomical units away from its parent star, whose mass is about 25% that of the Earth. If it does exist, and if this isn't another measurement error, a year on this planet lasts about 5 Earth days, and the surface temperature there could be 360 Kelvin or 87 degrees Celsius. Whether this space object is really there or not remains an open question, and additional confirmations are called for. Alpha Centauri has been listening to our radio signals for over 100 years now. But the 40 trillion kilometers of space vacuum between us are too overwhelming for us to cover at this point. It takes light over 4 years to get there, but for humans such speeds are still in the realm of fancy. Even today's swiftest state-of-the-art spacecraft would need tens of thousands of years to cover this distance. However, application of advanced technologies could theoretically greatly reduce travel time. Since the very dawn of space exploration, projects of a great number of spacecraft have been suggested that hypothetically would have been able to negotiate interstellar distances. Nevertheless, not a single one of them has been actually designed. Most of these would-be missions were forgotten, but one is still under active consideration. This is the Breakthrough Starshot program, which implies sending as many as 1,000 microprobes to Proxima Centauri as soon as in the first half of this century. They will not measure over a centimeter in size, and special thin and durable sails are planned to be created to aid the probes along. The sails will be blown out, as it were, by impulses of a highly powerful Earth-based laser. Estimates show that an interstellar probe like that is going to be leaving the solar system at a speed roughly 20% that of the speed of light, with the overall travel time around 20 years. After that, it will take another 5 years or so for the data collected by the mission to reach the Earth. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from the Earth. Some of them are single stars, while others contain 2 components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks made up of gas and dust, where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environs. As we slowly recede from our home planet, we will cover dozens of light-years of space and visit quite a few remote worlds. It is time to set out to the stars. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation GJ699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 3134 Kelvin, or slightly under 2900 degrees Celsius. With these characteristics taken into account, it isn't surprising that the object's luminosity is 2300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object, but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at the time was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever. Leaving the vicinity of Sirius, permeated by lethal ultraviolet radiation and stellar wind, we will perform a maneuver near the solar system to reach a small star 14 light-years from the Earth. It is designated differently in different catalogs, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3272 Kelvin, or about 3000 degrees Celsius. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system near us. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first and closest exoplanet to the parent star is called Wolf 1061b. It is located 0.038 astronomical units from the center of the system and completes a full orbit around it roughly every 5 days. The object has a mass in the range of 1.5 to 2 Earths and a radius 20% greater than that of our planet. It is likely that the celestial body is tidally locked and faces its star with one side at all times. For this reason, the temperature on the day side of the planet is extremely high, and the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanet completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes a full orbit around it roughly every 18 days. Thus, it is within the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 3 to 4 times more massive than our planet and belongs to the class of super-Earths. Observations show that its radius is about 1.6 times that of Earth, while the gravity on its surface is calculated to be 60% higher than what we're used to. The exoplanet receives noticeably less energy from its star than the Earth does from the Sun, so its temperature of equilibrium is much lower. It is 223 Kelvin, or about 50 degrees Celsius below zero, which is slightly higher than on Mars. Nevertheless, given variations in temperature during the day and from season to season, liquid water may well exist on the surface of the celestial body. With a dense atmosphere with a pronounced greenhouse effect, this probability is even higher, and conditions on the planet could approach favorable ones. Of all the potentially habitable exoplanets known to date, Wolf 1061c is one of the closest, ranking 5th on the list. The third object in the system is called Wolf 1061d. It follows a clearly elongated orbit, with the distance between the parent star and the aphelium reaching 0.73 astronomical units. As for the perihelion, it lies much closer to the system's center, just 0.21 astronomical units away. It takes the celestial object about 217 Earth days to complete a full year rotation. The mass of Wolf 1061d is calculated to be roughly 7.7 times that of our Earth. If this celestial body turns out to be a rocky object, its radius is supposed to measure about 1.7 times that of the Earth. If, on the other hand, this planet falls in the category of mini-Neptunes with a thick multilayer atmosphere, its diameter is supposed to be not less than 2.2 times that of our planet. In spite of a comparatively high eccentricity of its orbit, Wolf 1061d never enters its star's habitable zone. The celestial body is likely to be completely unsuitable for supporting life, but may pose a great scientific interest in terms of planetary evolution. This system is one of top priority destinations for future explorations, and it is highly probable that there are new discoveries to be soon made in it. In addition to everything else, the star Wolf 1061 is also remarkable for its position, which is virtually at the very edge of the so-called local interstellar cloud. It is an area in space filled with hot but extremely rarefied hydrogen. Its temperature measures about 7,000 Kelvin, and on average there is just 0.3 of an atom to be found in 1 cubic centimeter of space here. It is about twice as little as the average value in the Milky Way. The solar system has been moving through the local cloud for the past 10,000 years. Its average diameter is about 30 light-years, but our system is almost at its very edge. Alpha Centauri, for example, is already in the neighboring so-called G-cloud. We, on the other hand, will spend about another 2,000 years within our cloud, after which we will enter an even thinner and hotter region. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has a momentum of its own, which is perpendicular to the direction of the solar system's motion, and also has a magnetic field and radiation. Fortunately, despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to organisms on Earth. The solar wind is a reliable protection against cosmic hydrogen, and the Earth's dense atmosphere takes the hit of particles that do break through the heliosphere. Still, traces of the isotope Iron-60, also called interstellar iron, have been found in the ice of Antarctica. It is thought to have arrived to Earth from no other place but the local interstellar cloud. As we continue our journey through space, we will soon get to a rather unusual star called AP Columbae, located 27.4 light-years away from Earth. First and foremost, it draws our attention because it was born just 40 million years ago, when the dinosaurs would have long since died out on our planet. What is even more striking is that its birth took place in a completely different region of the galaxy, 450 light-years from the object's present position. Young stars usually remain close to their stellar nursery for quite a long period of time, up to several 100 million years. If you analyze the movement of AP Columbae, however, you will find that it probably previously belonged to the open cluster IC2391. The cluster has about 30 stars, united by a common origin and direction of movement. But a few million years ago, one of them exploded, shattering the delicate equilibrium of a multitude of cosmic bodies. This catastrophe gave the young star an additional momentum that swiftly expelled it from its birthplace. A very small red dwarf with a mass just 13% that of the Sun, this star emits 4 times more energy than any other known celestial body with the same parameters. In addition, its radius is twice as large as calculated based on the modern stellar structure theory. Strangely enough, another unusual feature of the star has helped to provide answers to these riddles. According to spectral analysis of its radiation, the stellar matter of AP Columbae contains an abnormally large amount of lithium. Normally, this element is found in abundance in protostellar clumps, but it burns out completely after the start of a thermonuclear reaction. This means that the star is very young and at the very beginning of its formation, not even in the main sequence phase yet. As a consequence, AP Columbae is unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, during which its luminosity may increase by up to 10 times for a short while. Such events would normally threaten exoplanets nearby, stripping off their atmosphere and sterilizing their surface with ultraviolet radiation. As it is, observations show that there are no large space objects within 4.5 astronomical units of this star. In all likelihood, it is too young for the formation of fully fledged planets. Nevertheless, it is a unique cosmic body, very important for understanding early evolutionary stages of stars. As we've seen, not every star has a planetary system, so our next stop is near the orange dwarf Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, designated Gliese 370b. The object was discovered with the use of the radial velocity method and has a mass of 3 to 4 Earths. According to current understanding of the formation of celestial bodies, the discovered world is most likely a rocky planet, with a radius about 30% larger than the Earth's. Under such conditions, the gravity on its surface may be at least 40% higher than what we're used to. Gliese 370b is located at a distance of 0.26 astronomical units from its parent star and completes an annual rotation in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the albedo value of its surface is close to that of the Earth, then the average temperature of the celestial body should be about 25 degrees Celsius, which is a few degrees higher than on our Earth. The fact that an exoplanet is located quite far from its parent star suggests that it is not tidally locked and has its own diurnal cycle. This contributes to an evener distribution of heat over the surface of the celestial body, which as a consequence may create a milder climate. A moderately high gravity should smooth out the planet's terrain, which combined with an abundance of liquid water may cause vast seas to form, both warm and shallow. Such places have traditionally been considered the most comfortable for the genesis and support of life. At the time of its discovery, Gliese 370b was considered one of the most favorable exoplanets for potential biological life. However, more recent research has suggested that conditions on its surface are somewhat less attractive than previously thought. In particular, the atmosphere of the celestial body may be too dense and have a pronounced greenhouse effect. Still, even according to the most pessimistic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius, which corresponds to a temperature range of about 30 to 100 degrees Celsius. Given that our planet's climate was about the same during the Archean period, Gliese 370b remains a very promising exoplanet for the search for extraterrestrial life, which means that its exploration must continue. If we stop and look around for a while, we will find that we have already traveled more than 50 light-years away from our solar system. There are over 1,000 stars within its radius, most of them single stars. Others are binary stars or even groups of stars. The most striking example is Castor, a complex and surprising system of as many as 6 components. This stellar system is located 50 light-years away from Earth and is visible to the naked eye as a single source of light. As the second brightest object in the constellation Gemini and the 23rd brightest in the night sky in general, Castor has been known to humans since ancient times. As the system has as many as 6 components, it has a rather complex structure. The 2 brightest of these, Castor A and B, are bluish-white Sirius-like stars, each with a red dwarf companion nearby. The distance between the mass centers of these binaries is about 110 astronomical units, and it takes them 445 years to complete a full orbit. About 600 astronomical units from Castor A and B, there is another compact binary system, consisting of a pair of almost identical red dwarfs. Each has a mass of about 0.6 times that of the Sun and has a surface temperature of about 3,900 Kelvin. The two stars are so close together that they take less than 20 hours to complete a rotation. They move around the system's common mass center following a very oblong elliptical orbit with an orbital period of about 14,000 years. So far, no confirmed exoplanets have been found in the Castor system. But if they do exist, they're most likely to be located here, near the faintest component of the system. In 2018, for example, astronomers detected variations in the orbital period of Castor C, which implies there may be a brown dwarf nearby, about 49 times more massive than Jupiter. According to calculations, it is located 14 astronomical units from the parent star and completes a full orbit around it every 54 years. It is possible that, like many red dwarfs, Castor C has rocky exoplanets close by. In this case, the skyline of such a hypothetical object must present a truly incredible spectacle. On one side, a considerable part of it is occupied by two crimson stars circling the sky without stopping, while on the other side, the eternal twilight is diffused by the light of a pair of stars, either of them hundreds of times brighter than the Earth's moon. Whether this is actually the case cannot yet be verified at this point. Although the stars we have visited are great distances apart, they are all within a single structure stretching for the total of about 300 light-years. This is called the local bubble and contains not only thousands of stars, but also several large structures, including the local interstellar cloud. The local bubble was formed by successive explosions of several supernovae that occurred between 10 and 15 million years ago. It is a giant cloud of interstellar gas heated to 1 million Kelvin. Because of its high temperature, the gas tends to expand, so its density is about 10 times lower than the galactic average. In addition, the hot ionized hydrogen constantly emits X-rays. Fortunately, the magnetic fields of the Sun and the Earth, as well as the atmosphere of the planet, successfully protect us from the harmful radiation. The local bubble is bordered by other similar formations. For example, slightly away from the direction of the solar system's motion is the so-called Bubble 1, formed by supernova explosions in the vicinity of Antares. This giant cosmic structure has been actively interacting with our bubble for a long time, which has caused the formation of tremendous compactions located at the region at the edge. The center of the neighboring bubble is about 500 light-years from us, and the solar system will reach its margins in a few tens of millions of years. Assumptions about the existence of space objects the size of a planet, which are independent from any star, have been around for a long time. Such celestial objects, freely drifting around interstellar space, are referred to as orphan, free-floating or rogue planets. Astronomical bodies of this kind emit very little thermal and light energy into space around them. It is suggested that there are no bodies in their close proximity they could clearly interact with or be bound to. That is why it is hardly surprising that these objects are so difficult to detect. The first potential representatives of this class of planets were spotted as recently as in the early 21st century. The warmest rogue planets can be detected with infrared telescopes, and others thanks to something called the gravitational microlensing effect. As one would expect, this class of celestial objects is one of the most mysterious and understudied. Today, only 3 astronomical bodies can be classified as rogue planets with a sufficient degree of certainty, with the overall number of rogue planet candidates over 24. Incidentally, according to the analysis of data collected in the course of the Ogle project, the Milky Way may supposedly be home to up to 100 billion objects of this class. This may only mean that right now we're at the very beginning of an upcoming series of discoveries in this field. Our notions of what rogue planets are like have long been based purely on assumptions and hypotheses. With the technological advancement of highly sensitive observation equipment, there arose opportunities to put them to the test in practice. The rogue planet lying closest to the Earth among those already confirmed is known as WISE 0855-0714. 7.27 light-years away from the Sun, it was detected in 2014 with the WISE Orbital Infrared Telescope. The astronomical body cannot be seen through optical telescopes, as it emits no visible light to speak of. The reason for this is its extremely low temperature, from 225 to 260 Kelvin, or 48 to 13 degrees Celsius below zero. In terms of its parameters, it resembles a cooled-off gas giant, and its age cannot be under 1 billion years. The rogue planet is mostly made up of hydrogen. However, in 2016, the Gemini Observatory produced evidence of the presence of large amounts of water in its atmosphere. It is suggested that water is condensed into clouds made up of tiniest particles of ice. Today, it hasn't been established for certain how this object came to be. There are currently 2 versions suggested by researchers. According to the first one, a celestial object like that starts its life cycle in the protoplanetary disk of a regular planetary system. Mathematical modeling of this process shows that if the original cloud of gas and dust is heavy enough, it is highly likely that at least one planet will be ejected beyond the system. The celestial object may also be forced out of its star's environs if another massive star passes it by, or else if its planetary system collides with another system. The chances of events like that are admittedly comparatively small. The other version has it that the space object was born just like any other star on compression of interstellar gas. At the same time, the mass of the object proved to be too small to unleash any thermonuclear reactions in its interior. It goes without saying that in this manner, it may turn out only as a gas giant or a brown dwarf, but not a rocky planet similar to the Earth. Some researchers don't agree that these objects should be seen as rogue planets and classify them as sub-brown dwarfs instead. Others suggest using the term planemo for all interstellar wanderers that don't show any thermonuclear activity. Bearing in mind today's notions of the makeup of brown dwarfs and gas giants, we may estimate the mass of WISE 0855-0714 at anything from 3 to 10 Jupiter masses. This rather falls short of starting a thermonuclear reaction, but quite enough to keep the heat effectively trapped inside the planet. Taking into account our knowledge about natural laws, we can predict what the conditions on the astronomical body's surface are like. For example, according to research by David John Stevenson from the University of California in the US, gas giants similar to Jupiter don't cool off instantly after receding from their star. Their thick hydrogen atmosphere is quite reliable thermal isolation, while the dense and hot nucleus made up of metallic hydrogen can keep the planet heated for a considerable time. Estimates show that the temperature of the lowest strata of a hypothetical celestial object's atmosphere may be high enough for liquid water to be around. It is likely to be present in the atmosphere as giant clouds made up of tiniest droplets. These deductions agree with the results of mathematical modeling of WISE 0855-0714 carried out by a team of scientists from the University of Edinburgh. It showed that the most likely temperature value of the planet's surface is 250 Kelvin or 23 degrees Celsius below zero. The celestial body's atmosphere also has a comparatively warm layer around 100 kilometers thick, whose density fluctuates from 0.4 to 1.2 milligrams per cubic centimeter. It is comparable with the conditions on the Earth, and so it is thought that this environment should be favorable for potential organic life. Incidentally, a planet doesn't have to be a massive gas giant to avoid freezing in the cosmos. In 2020, a rogue planet candidate was detected using gravitational microlensing techniques. And here is the long designation it got. It is still awaiting confirmation of the rogue planet's status, and its parameters have been defined only generally so far. According to preliminary data, however, the object is comparable to the Earth in terms of its mass, and is anything from 30 to 180,000 light-years away. According to our current scientific notions, an object with a mass like that is not supposed to be a gas giant, and is more likely to be a rocky planet. This, in its turn, offers good grounds to believe that the object formed in the protoplanetary disk of a planetary system as the latter was forming. It may have been ejected from the system as a result of a cataclysm in space, or alternatively, under the influence of a larger neighbor. After that, it was left to its own devices and so became a free-floating planet. What will happen to it next is predefined by a combination of several factors. Provided the object's atmosphere is sufficiently dense, it will be reliably thermally isolated. Potentially, a layer of ice on its surface could produce the same isolating effect. In addition, with the object's interior scorching hot and with radioactive elements undergoing decay, most of the hypothetical ocean will remain in a liquid state. If the planet happened to have a moon, it may have retained it on ejection. If this is the case, tidal forces are likely to continue to deform and warm up the lithosphere. Theoretically, with any luck, primitive anaerobic life forms may have stayed around, although of course it would be next to impossible to discover their traces now. Most of the data about the rogue planets we know today were arrived at following mathematical modeling and complex calculations. It was possible to do these calculations thanks to the tiniest bits of information gleaned with the help of orbital and Earth-based telescopes. Even as I speak, a project is being worked on known as Cleopatra. Its main objective will be to search for free-floating planets and other objects in space with subsequent definition of their parameters. The project relies on something called microlensing. It is a phenomenon when a celestial body passes between a remote star and the observer on the Earth and briefly interferes with the light emitted by the remote star in the background. When observed from different angles, the moment of transition will be registered a fraction of a second sooner in one observatory than in another. Referred to as lensing parallax, this effect allows scientists to gauge the distance to a detected object as well as its mass and dimensions. An interplanetary spacecraft is planned to be created within the project. It is supposed to blast off the surface of the Earth as soon as in 2025 alongside a mission to Mars, after which it will enter its own orbit around the Sun. The project will be aided by a specialized artificial intelligence component, whose mission will be to process and analyze collected information. The Cleopatra project will certainly delight us with a wealth of exciting and important information, so there is a lot to look forward to. What is to become of all those rogue worlds out there, drifting quite by themselves in the dark depths of the universe? In theory, an orphan planet may be captured by the gravitational field of a star and become part of its planetary system, but this chance is by all accounts minuscule. Most objects like that are destined to wander for billions of years through endless expanses of space while slowly and inevitably cooling off. Eventually, they're to be swallowed up by black holes or else destroyed as a result of a cataclysm in space, never to reveal their secrets to mankind. It goes without saying that to detect a celestial object that absorbs all light shed on it is a challenging task, to say the least. That is why there are not that many confirmed black hole candidates today. Still, mathematical modeling shows that their number in our galaxy may reach 100 million. This may seem an incredibly big number, but since there are 200 to 400 billion stars in the Milky Way, it makes us realize that in all these expanses, black holes are objects one doesn't come across that much. In one of our previous videos on the topic, we mentioned that a star, the progenitor of a black hole, has to have a mass of at least 18 to 20 solar masses. Only this will ensure a powerful enough supernova to compress the scorching hot core of the star to an exceptionally dense clump of material. After this has occurred, nothing will be able to stand up to the object's gravity force and escape beyond the boundaries of a conventional sphere predefined by the so-called Schwarzschild radius. What used to be a star transforms into a bizarre object with an inner makeup that would defy description by the physical laws we're familiar with. The object referred to as A0620-00 or V616 is one of the black holes closest to our Earth that we know of. It lies 3,300 light-years away from our planet and forms part of a binary star in the constellation Monoceros. The other object in the system is an orange dwarf with a mass half that of the Sun. Every 7.75 hours, it completes a full orbit around an invisible object of unknown nature. Estimates show the mass of this invisible object to be around 6.6 times that of the Sun. It is admittedly too much for a neutron star. This leads one to believe that the bizarre invisible object is more likely than not a black hole. In addition to getting deformed and elongated by the more massive neighbor's gravity, the orange dwarf is also getting stripped of the outer layers of stellar matter. Spiraling streams of scorching gas gradually flow to the black hole and form a bright accretion disk. It is thanks to this dazzling disk that the black hole was detected. There are at least several dozen stars in the environs of V616, some of which almost certainly have their own planetary systems. It is highly likely that in the future, one of these stars will get dangerously close to the black hole and as a result will be sucked in by the object's insane gravity. This unfortunate star will have no choice, and in this case, the same slow demise is eventually awaiting the black hole's new companion as that of its current one. The process of interaction of a black hole with other objects largely depends on their mass ratio. The smaller the distance between them and the more massive the black hole, the stronger the influence of its tidal forces over its companion. The star may be deformed by them and get stretched towards the system's common mass center. They can also form channels that would carry stellar matter closer to the black hole, adding up to its accretion disk. If the tidal forces happen to be strong enough, they may well destroy the object that is being sucked in by turning it into a fiery ring. It is assumed that there may be planets orbiting a black hole, just as if it were a regular star. In contrast to a widespread opinion, black holes are actually not able to suck in all objects around them indiscriminately. From the point of view of gravitation, in astronomical terms they behave just like any star with the same mass. That is why, incredibly though it may seem, a black hole may well have a stable planetary system. There are several ways for them to form. Firstly, new celestial objects may originate in a nebula of gas and dust that is formed after a supernova. Influenced by gravitation, they first form clumps of material that collide with each other and attract cosmic dust. As a result, they eventually turn into planets and satellites, as well as large numbers of small celestial objects like asteroids and comets. The radiation of the black hole's accretion disk may be powerful enough to warm them and even melt ice on their surfaces. Hypothetically, a planetary system like that could be favorable enough for life to originate and, with any luck, evolve. Secondly, when a black hole captures and destroys another planetary system, some of its objects may choose to take up stable orbital positions around their new host. Of course, this makeover would bring about dramatic changes on the celestial object's surfaces. Thus, an ice giant may transform into an ocean planet, and a gas giant may lose almost all of its hydrogen and turn into a Chthonian planet. Thirdly, space wanderers like rogue planets or interstellar asteroids may also be ensnared by the massive object's gravity. Even though systems like that have not yet been discovered in practice, there is no reason to suppose they are non-existent. If, on the other hand, a planet is too close to the system's center, and the black hole is massive enough, other factors come into play. A scorching hot stream of material forming the accretion disk will strip the celestial object of its atmosphere, and its friction will slow it down and pull it still closer to the black hole. Eventually, extremely powerful tidal forces will rip the planet to tiny shreds. The debris will be pulled into the accretion disk and gradually melt in the hot gas around. In the end, they will inevitably get swallowed up by the black hole and in essence become part of it. It is posited that there are three main types of black holes to be found in the universe that are different first and foremost in terms of their mass. The first type can be found in the center of most spiral galaxies. These are gargantuan black holes with masses reaching several billion solar masses. The density of matter in the central part of a galaxy is generally extremely high, which is the reason why there originates a big number of large and bright stars quite closely packed. As they rapidly burn out, they transform into black holes, which in their turn rapidly grow and often merge with each other. As a result, supermassive objects are born, which are surrounded with giant accretion disks made of scorching hot material. They illumine space so brightly that it makes them seen from billions of light years away, even if their galaxy is completely unobservable to us. These objects are known as quasars. The second type is much more widespread, but at the same time, black holes like these are not that easily detectable. Their masses are close to those of stars, and they form out of large stars at the end of the latter's life cycle. By devouring other celestial bodies and interstellar gas, these objects gradually gain in size and eventually turn into intermediate mass black holes. They can also merge together, which generates gravity waves that distort space many light years around. The third type is the hypothetical primary black holes. Their existence has been inferred from today's theory of universe's origins and evolution. Fluctuations in matter that filled space in its early stages of evolution may have been favorable for black holes of infinitely small size to originate. It should be mentioned that according to estimates, the smaller an object of this type, the faster it evaporates, and at the end of its life cycle it turns into a tremendously powerful electromagnetic impulse. Modeling shows that primary black holes with masses around 10 to the power of 12 kilograms are supposed to be flaring up sometime around now, but to date, no such event has been registered yet. According to a certain hypothesis, a microscopic black hole may form on collision of extra high-energy elementary particles. This variety is referred to as quantum black holes. Still, the conditions necessary for such an event to happen are impossible to be reproduced in lab conditions, and estimated life expectancy of these hypothetical objects is so small that it can hardly be measured with today's latest and most advanced methods. That is why quantum black holes still officially exist only in theory. Of course, it is extremely difficult to detect such dark and compact objects. Some of them happen to have a star companion, whose anomalous trajectory of movement gives telltale prompts of there being an invisible thing in close proximity. Another popular method of detection is observation of accretion disks. These object spectra have some typical features that allow telling them from other sources of light in space. Sometimes we're lucky enough to get a snapshot of a disk with a black spot in it that is evidence that the observed object's structure is quite unusual. A black hole may also be detected thanks to the gravitational microlensing effect. This involves detecting the massive invisible object as it transits between the Earth and a remote star. This changes the star's spectrum in a special way. But admittedly, this method requires a number of rare factors to successfully work. There is hardly any doubt that space is filled with great numbers of objects that are dark and not easily noticeable. There may be wandering black holes among them. These mysterious objects, roaming around in interstellar space and absorbing every bit of light they come across, will probably never reveal their secrets to us. Long before telescopes had been invented, people could observe a light strip crossing the heavens. The fascinating and mysterious phenomenon prompted a multitude of legends, but it took thousands of years of scientific progress to finally account for it. It turned out that the Milky Way wasn't a path of gods. What it is the dissipated light of billions of stars too remote to distinguish each one separately. The idea of the stars around us making up part of a single structure of enormous dimensions was first suggested by Immanuel Kant back in 1755. He also assumed that some nebulae discovered by scientists could in fact be remote star clusters, that is, other galaxies. This ingenious guess was well ahead of its time, with the philosopher's contemporaries initially dismissing it. Only in the early 20th century did the progress of observation equipment enable scientists to confirm the existence of other galaxies, and in 1936, Edwin Hubble devised a classification system. Many of its principles are still referred to by scientists today. According to this system, the Milky Way falls into the category of barred spiral galaxies, although it took a long while before it had assumed its today's looks. Our galaxy is quite an old one, since the stars in its central globular clusters were born as far back as around 13 billion years ago. At the same time, there are some areas in the Milky Way where stars are actively born, which means that there is always a fresh supply of young stars. The collected data points to the fact that the Milky Way is a comparatively large galaxy in astronomical terms. The diameter of its disk measures as much as 200,000 light-years. With a halo reaching out into space much deeper yet, our galaxy is home to at least 200 billion various stars, as well as 25 to 100 billion brown dwarfs. In addition, it contains over 1 trillion planets, countless small celestial objects, as well as clouds of cosmic dust and interstellar gas, which may reach gigantic dimensions. At the same time, regular matter accounts for a small ratio in the galaxy. Around 90% of the Milky Way's overall mass is the so-called dark matter. The amount of light emitted by this mysterious and widespread substance is negligible. However, dark matter plays an active role in gravitational interaction. Even though most of the galactic mass remains invisible, we can still calculate it. To that end, scientists refer to stars' trajectories of movement around the center of the Milky Way. According to the estimates, the overall mass of our galaxy reaches 0.8 to 1.5 trillion solar masses. The structure of the Milky Way is quite elaborate. We'll start our journey today from its center. This area of the galaxy is shrouded in massive clouds of gas and dust, but by happy chance we can observe it through the so-called Bardes window, an area of space with lower amounts of dust. Just like most spiral galaxies, the Milky Way has a supermassive black hole in its center, which is surrounded with an accretion disk with a radius roughly 3 light-years. Dubbed Sagittarius A star, it is the closest object of this class to us. Its mass is 4.3 million solar masses, and its radius isn't over 16 million kilometers, which is 3 times smaller than Mercury's orbit. The first data about the nature of the object in the center of our galaxy was acquired in the course of long observations and thorough calculations. Only as recently as on May 12, 2022 was it possible to get the first image with the help of the EHT network of radio telescopes, and so the earlier hypotheses were confirmed. The area in the center of our galaxy is highly populated. More than 6,000 stars have already been detected within 3 light-years from the black hole, with the orbits of some of them defined rather accurately. For example, there is a white-blue star, designation S62, which is 17.8 astronomical units away from the black hole on its closest approach to it, while moving at 6.7% the speed of light. Classical mechanics laws are inadequate for description of the trajectory of movement of a star as swift as that because of relativistic effects. Just to illustrate, the axis of its orbit shifts by 75 angular minutes with every completed orbit. Besides, when crossing this area in space, we can see several large star clusters with a total mass of around 1 million solar masses. And slightly further, roughly 200 light-years away, another massive black hole is likely to be lurking, whose mass should be around 100,000 times that of the Sun. Traveling further on, we will reach the central molecular cloud, an irregularly shaped area measuring 1600 to 1900 light-years, whose mass is over 60 million solar masses. There are a great many stellar nurseries and gas nebulae, as well as protostars and remnants of supernovae. Most of the cloud's matter is dense hydrogen, whose temperature fluctuates between 50 and 600 Kelvin, which corresponds to 223 degrees Celsius below zero to 327 degrees Celsius above zero. Spectral analysis shows the gigantic nebula to contain carbon monoxide, methyl alcohol, and hydrocyanic acid in addition to hydrogen. Having receded from the Milky Way's center a bit, we will see that it is encompassed by a bulge, a bright and massive formation of an elliptical shape. With its length reaching 10,000 light-years, its transverse diameter is roughly 7 light-years. The total mass of the bulge is as much as 10 billion times that of the Sun. The exact number of the stars cannot be calculated because their radiation blends and renders any estimates unrealistic. Being elongated, the bulge forms the so-called bar stretching for approximately 13,000 light-years and serving as the base for spiral galactic arms. It is here, at one of its ends, that we can see the star cluster Stephenson 2, containing the largest known star today. Its designation is Stephenson 2-18, and its radius is 2,150 times that of the Sun. Unfortunately, chances of finding exoplanets orbiting this outstanding object are quite minuscule. Even if planets did exist at some point in the past, the hypergiant would have swallowed them up while it was expanding. The galaxy's center is home to billions of stars and apparently a great number of exoplanets. Chances of encountering a potentially habitable world among this great multitude are much lower than in less populated areas of the galaxy. This is due to the fact that when a big number of stars are located close together, they destabilize exoplanets' orbits, while their powerful radiation is lethal to all living things. That is why a special area in the galaxy is defined as the habitable zone. It looks like a ring, with a radius measuring 22 to 29,000 light-years, and contains star systems with the most favorable conditions for the genesis of biological life. Worlds encompassed by the ring languish in exposure to excessive radiation, while beyond the ring there's a lack of heavy elements. However, mathematical modeling shows that stars within galaxies are able to migrate thousands of light-years away, thus either leaving the habitable zone or entering it. Consequently, with an exoplanet lying within the zone, it does not automatically suggest favorable conditions on it. Moving on away from the center of the Milky Way, we will have a chance to check out its most impressive part, the galactic disk. It is made up of two components with different properties. The first one, known as the thin disk, measures 1,000 to 1,300 light-years in thickness, and its visible radius measures as much as 50,000 light-years. On the edge, it gradually dissipates, with the outermost stars lying up to 100,000 light-years away from the galaxy's center. This part of the Milky Way contains around 80% of the galaxy's visible mass, and in fact, it was the last component to have formed. As for the thick disk, its diameter is comparable to that of the thin disk, but it's 4 times as thick and is much more rarefied. It is made up of old stars and is practically devoid of interstellar gas. Observations of some stars in the Milky Way, as well as mathematical modeling, show our galaxy to have swallowed up another one in the period from 11 to 8 billion years ago. This hypothetical cosmic structure was dubbed Gaia Enceladus. It is thought that it contributed several billion stars to the Milky Way, as well as great amounts of interstellar gas and dark matter. It is thanks to this tremendous event that most of our galaxy's thick disk formed, and an additional supply of gas led to a stellar baby boom. There is no doubt that spiral arms are the most noticeable structural elements of our galaxy's disk. Usually 2 major ones are singled out, the Scutum Centaurus arm and the Perseus arm, and 2 minor ones, the Norma arm, and the Carina Sagittarius arm. Sometimes a fifth large arm is taken into account, named after the Cygnus constellation. Galactic arms are areas of especially high star count. Most of interstellar gas is also concentrated here, which is why the rate of star formation in the arms is 3 to 5 times higher than in the galaxy on average. They spend the first millions of their lives in open clusters, but gravity forces are too weak to hold the stars close together for a long time. This destabilizes the clusters, and young stars gradually drift away from each other. Traveling along the Carina Sagittarius arm, we will reach a fork that links it to the Perseus arm. The length of this stellar structure reaches 11,000 light-years, and its width measures roughly 3,500 light-years. It is referred to as the Orion arm, and it is here, 27,000 light-years away from the galaxy's center, that the solar system is located. From our planet's perspective, the galaxy's center is seen as a dark abyss. This is the Great Rift, an area of space that shuts out the greater part of the Milky Way from our gaze. It is filled with massive clouds of interstellar gas and dust, and its total mass is as much as 1,000,000 times that of the Sun. Even though the Great Rift is practically not transparent in the optical range, its matter actively emits radio waves and thermal energy. Spectral analysis data reveals that the clouds are mostly made up of hydrogen with a small percentage of more complex compounds, ammonia, alcohols, and amino acids. The Great Rift is thought to be a potential stellar nursery, but it is going to take a while until the first stars light up in that area. While it is still not quite active, let's move on, beyond the galaxy disk. Even though its bright and clearly defined arms attract a lot of attention, there is more to the Milky Way than that. If we look closer, we will see the vastest and the most rarefied of its components, the halo. Its visible part, spherical in shape, stretches for up to 260,000 light-years away from the galaxy's center, but accounts for just a few % of the total mass. The halo contains a great number of globular clusters made up of remarkably old stars over 12 billion years of age and several tremendous stellar streams. The Sagittarius stream, for example, made up of several thousand stars, encompasses our galaxy in an elongated ellipsis, which is almost perpendicular to the main plane. Modeling shows that all these stars are highly likely to have been gravitationally captured by the Milky Way from a dwarf satellite galaxy, designation Sagittarius DEG. It lies 500,000 light-years away from the Milky Way's center and is going to be swallowed up by it completely within several billion years. Another dwarf galaxy has already met a similar fate. Lying in the Canis Major constellation, it was almost destroyed by the Milky Way, which pulled out millions of its stars by gravity forces. Stretching for 200,000 light-years and mixing with other stars, this string of stars with a total mass of roughly 100 million solar masses has already wrapped around our galaxy 3 times. Apart from bright but rare stars and clusters, the halo contains great amounts of gas, whose temperature reaches millions of Kelvin. Also, great amounts of dark matter are thought to be scattered in the vicinity of the Milky Way, forming the so-called dark halo. Stretching for up to 2 million light-years, it hardly emits any electromagnetic radiation and can be detected only by gravitational interaction. The dark halo remains an unsolved mystery, yet it greatly contributes to the global stability of our galaxy. $2,500,000 years ago, the Andromeda Galaxy. A giant star expires close to the galactic core. The last seconds of its life pass in an explosion of tremendous force. Trillions of tons of red-hot plasma explode in a huge cloud, turning the nearest planets and satellites to dust. powerful electromagnetic impulse pierces outer space in all directions. Millions of years later, it is to reach the Earth. The year 1885. The planet Earth. The attention of all astronomers on the planet is focused on an amazing astronomical event. A remarkably bright flare in the region of the Andromeda Nebula briefly eclipses the nearest stars with its radiance. This amazing supernova is dubbed as Andromeda, and its anomalous parameters baffle astronomers for a long time. But just 6 months later, the star rapidly dims and soon disappears from the sky forever. Unfortunately, at the time of the flare, generally accepted notions about the structure of the universe were far from those of today. At that time, astronomers were not yet able to measure distances to cosmic bodies, so the bright spot in the constellation Andromeda, also known as object M31, was considered an ordinary reflection nebula on the outskirts of the Milky Way. Meanwhile, with the advent of new, more powerful telescopes and the development of space technology, the situation gradually changed. As soon as in the 1920s, observations by Edwin Hubble and other astronomers proved that the Andromeda Nebula is a different galaxy, much like the Milky Way. About a century has passed since then, and science has moved far ahead. It is currently known that the Andromeda Galaxy has a spiral structure and comprises about 1 trillion stars. As for its diameter, it exceeds 150,000 light-years, and its mass is relatively small and ranges from 800 billion to 1.5 trillion solar masses, about the same as the Milky Way. This is thought to be the case due to the abundance of red dwarfs and less dark matter in its composition. Like all spiral galaxies, Andromeda has a massive nucleus at its center, made up of millions of closely spaced stars. Its radiance is so great that it dazzles observation instruments, making it impossible to distinguish individual stars. On account of this, the remnants of the 1885 supernova, known as S Andromeda, have long been impossible to trace, although surviving records clearly indicate that it exploded near the center of the galaxy. It was only in 1988, 103 years after the legendary flare, that a small nebula was detected at a small distance from the nucleus, a dark spot standing out against the background of the dazzling central region. With the help of spectral analysis and proper motion modeling, it was firmly established that it is a remnant of S Andromeda. Thus, this cosmic object became the first supernova detected outside the Milky Way. Careful study of the central part of Andromeda will clearly reveal its unique difference from other spiral galaxies. It is an unusual double nucleus, the origin of which is not yet fully understood. The brighter and larger part is located slightly away from the geometric center of the galaxy, and is a giant supercluster of many bright stars with a total size of about 7 light-years. The second part, on the other hand, is closer to the center and is noticeably dimmer and smaller, with a diameter of about 1.3 light-years. It is assumed that this region hides inside a supermassive black hole about 50 million times heavier than the Sun. The nature of such a strange phenomenon remains a subject of scientific debate. According to some assumptions, in the distant past, M31 absorbed and scattered a rather large satellite galaxy, and the bright region is a remnant of its core, According to other hypotheses, the center of Andromeda still has a single structure. However, it is separated by a band of opaque dust, creating an unusual optical effect. Due to the remoteness and inconvenient location of the galaxy in space, it is still impossible to collect enough data to confirm these hypotheses one way or another. Meanwhile, as we continue traveling through the central region of Andromeda, you can also spot one of the most mysterious objects in this galaxy. Here is its tongue-twisting name on your screens. The key feature of this celestial body is that it is almost impossible to see even in the most powerful optical telescope. However, everything changes if you use X-rays. In this part of the spectrum, this star is the brightest point in the galaxy. Observations show that the object is a system made up of two components, one of which is a low-mass neutron star. Its radius is only a few dozen kilometers, and it completes a full turn around its axis roughly every 3 seconds. The second star of the system is a larger object. Although it is relatively dim, it's most likely a red giant. Calculations show that the total mass of both components is not more than 3 solar masses, and the distance between them is very small. Every 4 hours, the neutron star is eclipsed by the other star, and this causes its luminosity to sharply drop, to recover its previous values later. It is also very likely that due to the small distance between the stars, the neutron star is gradually absorbing its companion, which is why its mass is constantly growing. According to calculations, this process will last several tens of millions of years, and eventually, the second star will be torn apart by tidal forces and turn into a bright and hot ring-like nebula. Incidentally, this amazing object is only one of the many stars densely surrounding Andromeda's core. Together, they form a massive bulge with a diameter of about 12,000 light-years, which has a noticeably elongated shape. Also, M31 has a pronounced bar, which however faces us with its narrow side and so is almost invisible to the observer on the Earth. According to calculations, the bar's length measures about 17,000 light-years, with a width about 6,500 light-years. In total, about 30% of the Andromeda Galaxy's entire mass is concentrated in its central part. While we are gradually moving away, we can see that the edges of the bar serve as the basis for 2 giant spiral arms, majestic coils encompassing the center of the galaxy. At the same time, there are darker gaps between them, whose width is significantly larger than those in the Milky Way, reaching 13,000 light-years. Calculations show that the Andromeda arms contain about 56% of the galaxy's stellar mass, as well as some dark matter. Under the influence of gravity, interstellar dust and gas concentrate in the arms, forming numerous stellar nurseries, regions where new stars are born. Over time, these gas and dust clouds evolve into open clusters and associations containing a great variety of young stars. Their light is reflected and scattered by cosmic nebulae, endowing the galactic disk with an incredible, shimmering palette of colors. And in one of these clusters, there is a remarkable star dubbed AE Andromeda. It is one of the brightest stars in the galaxy and is a hot blue giant whose luminosity varies without any apparent pattern. Such objects are known as luminous blue variables and are extremely rare. Currently, only a few dozen are known. Because of the extremely high temperature and pressure, the outer layers of AE Andromeda are constantly in a state of unstable equilibrium, and the processes running in the interior of the star are largely chaotic and unpredictable. From time to time, streams of red-hot plasma collide with each other, generating extremely bright flares and enhancing the luminosity of the object by several dozen times. Hypothetically, the most powerful of them can increase the brightness of the star several million times. Such a phenomenon is called a supernova imposter and may occur at any time. Measuring the parameters of such a star, what with its instability and remote location, is an extremely difficult task. Nevertheless, with the help of modern ultra-precise telescopes, it turned out that the mass of A Andromeda lies in the range from 50 to 120 solar masses, and the radius at the peak of pulsations measures about 55 times the radius of our Sun, which is only slightly smaller than the orbit of Mercury. At the same time, its surface temperature is close to 20,000 Kelvin, and its luminosity is 500 to 700,000 times greater than that of the Sun. Just like all blue giants, A Andromeda generates remarkably strong stellar wind, whose speed, according to calculations, can reach 100 km per second. Because of this, the object loses about 2 quadrillion tons of matter per second, which means that its mass decreases annually by an amount similar to 10 planets such as Earth. However, for such a large star, it is almost imperceptible, because A Andromeda will complete its evolution much sooner than the losses incurred from the stellar wind will reach at least 0.1% of its mass. The fact is that despite its age of 2 million years, which is mere seconds by space standards, A Andromeda has already completed most of its life cycle. According to calculations, within the next million years, the star will go supernova, leaving behind a black hole surrounded by a vast gas and dust nebula. Speaking about the age of the stars, one cannot help noticing that they are scattered unevenly throughout the galaxy. Thus we can look into Andromeda's past and observe how it was being formed. The oldest stars, some 11 to 13 billion years old, are concentrated in the central part of the galaxy. In contrast, the disk and spiral arms mostly contain younger stars, ones formed about 3 to 4 billion years ago. Here, the numerous stellar nurseries contain pretty much baby stars, born only a few million years ago, which is practically seconds by space standards. This means that in the first stage of its evolution, M31 was much smaller in size, and its shape resembled an ellipse. Also, by analyzing the parameters of individual stars in Andromeda, it is possible to define an important, but at the same time rather conditional concept known as galactic habitable zone. It is believed that the concentration of stars in the central part of Andromeda, as well as the high level of radiation and unstable orbits of potential exoplanets, make this zone unfavorable for the genesis of life. At the same time, distant planetary systems located at the periphery of the galaxy are too poor in heavy elements, which implies that there are not that many Earth-like planets. Therefore, only the intermediate region of the galaxy can be considered hypothetically habitable. It is in this kind of zone, at a distance of about several tens of thousands of light-years from the center of the galaxy, that a small faint object known as Mega ML7 is located. It is a red giant, with a relatively small mass of about 50% that of the Sun. In 1999, thanks to a fortunate coincidence, astronomers were able to record the phenomenon of microlensing, during which they were able to study this inconspicuous and distant space body in more detail. The results of these measurements helped determine the mass and spectrum of the star, as well as the temperature of its surface, which was about 3,700 Kelvin. But the most important observation was the rhythmic deviation of the trajectory of the star from the main direction of its movement. Such oscillations are considered a sign of a possible presence of a fairly massive companion. The hypothetical object was dubbed Mega ML7b and is now considered a potential exoplanet. If the existence of this celestial body is confirmed, it will be the first exoplanet in the history of astronomy to be discovered outside the Milky Way. Information about this object is still rather scant, but calculations show that it is highly likely to be a gas giant. with a mass of about 6.3 times that of Jupiter. There are also reports that this system is likely to be as diverse as our own in terms of chemical elements, which means that there is a good chance of finding a variety of planet types within its boundaries. Not only gas giants, but also rocky celestial bodies similar to Earth. When we observe the Andromeda Galaxy, another striking feature that becomes immediately apparent is the great multitude of star clusters and associations, whose number is much bigger than in the Milky Way. In total, about 460 globular star clusters and about 10,000 open clusters are known to exist in M31, as well as several dozen large star associations. Some of them are concentrated in the center of the galaxy, others are scattered in a halo, and still other ones have settled right in its spiral arms. And one of the largest and most noticeable structures is NGC 206, a cluster located almost at the very edge of the galactic disk. Previously, this association was considered a globular cluster, but now, due to its size, it has received a higher status and is called a stellar association. In this region of space, with a radius of about 200 light-years, roughly 300 extremely bright stars and countless less noticeable ones are concentrated, with a total mass of about 200,000 solar masses. Their overall luminosity is so great that the association is visible from Earth in an amateur telescope, along with the core and arms of the galaxy. According to observations, NGC 206 formed after a merger of at least two large gas and dust nebulae separated by a dark band of interstellar dust. The age of one of them is about 10 million years. The other is noticeably older, having formed about 50 million years ago. The single giant nebula became a point of gravitational attraction for interstellar gas, which led to the formation of a great area of star formation. Over time, some of its stars will dissipate in the surrounding space, with the rest forming a large globular cluster. The galactic disk M31 contains many such formations, and not all of them originally formed within its boundaries. It is assumed that many large stellar associations are the remnants of major cosmic catastrophes of the past. According to calculations, throughout its entire existence, Andromeda absorbed more than 100 satellite galaxies. Some of them dissolved without a trace, while others turned into giant stellar streams. The collision with the object known to us as M32 may be considered the greatest. This compact elliptical galaxy is located above the Andromeda disk, only 17,000 light-years away from it. Its diameter is about 8,000 light-years, and considering its small size, the galaxy has a rather big mass, about 1 billion solar masses. In the center of M32, there is a supermassive black hole about 2.5 million times heavier than our star, which is surprising for such a compact object. In fact, M32 is just a remnant of a much larger galaxy that survived the Great Catastrophe. According to data from the Spitzer orbiting telescope, about 800 million years ago, a large satellite galaxy pierced Andromeda's disk at high speed, leaving a gigantic hole in one of the spiral arms. During this collision, M32 lost most of its stars, and it is unlikely to be restored to its former appearance. It is assumed that it could have been a full elliptical galaxy, or a small spiral galaxy, of which only the central part remains. In addition to M32, Andromeda has about 30 satellite galaxies connected to it by invisible gravitational threads. The brightest and largest of them is M110, which has a diameter of about 15,000 light-years. Most of the rest fall into the category of dwarf spherical galaxies and are located within 1 million light-years. Nevertheless, together they form the Andromeda subgroup, which is part of the local group. Its other members are the Milky Way and its surroundings, as well as the Triangulum Galaxy and some other objects. Inexorable gravitational forces are gradually pulling the local group towards a single center. That is why the Andromeda Galaxy is rapidly moving in our direction, covering over 300 kilometers every second. Distances from the Milky Way to other galaxies are by all accounts mind-boggling. As a rule, it is anything from millions to billions of light-years. Due to the universe's cosmological expansion, the distance between the Earth and any remote object in the universe is constantly growing, which makes the light emanating from this object look redder than it actually is. This phenomenon is known as a redshift. It is of great help in gauging distances and velocities on the astronomical scale. Alternatively, some galaxies' spectrum is blue-shifted, which means that they're not on an escape trajectory from us, but on the contrary are moving to meet us. One of these unusual space objects is the galaxy M86 in the Virgo cluster. Roughly 52 million light-years away from the Sun, it is moving towards the Milky Way at a speed of around 244 km per second, which makes it one of the fastest-moving blue-shifted galaxies. By moving at a high speed through the scattered gas the Virgo cluster is filled with, M86 is constantly shedding its own interstellar matter. As a result of this process, it leaves a trail of long lines of warm ionized hydrogen behind. M86 is connected with the almost destroyed spiral galaxy NGC 4438 with several of these filaments. These two galaxies are thought to have collided at some point in the distant past, which was the smaller one's undoing. Interestingly, M86 is known to have destroyed its other neighbors in the past as well. Several stellar streams have been detected in its halo that are likely to be the remains of smaller galaxies absorbed earlier. An impressive number of globular clusters in its structure is another outstanding feature of M86. Observations show that their number is upwards of 3,800, which is around 25 times as many as in the Milky Way. There is a theory that claims these clusters to be the remains of dwarf galaxies that M86 would have absorbed in the past. If it really is the case, then it would have destroyed tens or even hundreds of other galaxies. Having said that, M86 looks anything but unique. The galaxy ESO 137-001, which we'll be looking at next, has a similar shape. But unlike M86, it appears more outlandishly original. Located 227 million light-years away from the Sun, it is as heavy as 5 to 14 billion solar masses. As for its stars, most of them are young and bright blue giants. ESO 137-001 in its turn is part of Abell 3627, a large galaxy cluster. Moving to its center at an incredible speed of almost 2,000 km per second, the galaxy collides with interstellar gas pressure inside the cluster. As a result, its own gas is blown out, leaving behind tails that stretch for up to 260,000 light-years. Incidentally, the mass of interstellar gas in those areas is 2 to 4 times that of the gas inside the galaxy. It is hardly surprising that starbursts are a common thing here. That is, stars don't stop forming in these enormous streams made up mostly of hydrogen. When seen from the side, ESO 137-001 appears like a giant jellyfish floating through endless expanses of space. Unfortunately, as the galaxy is continuously stripped of its interstellar gas, its life expectancy diminishes too. With not much material left, no new stars can form here, which greatly affects the structure of the spiral arms and central bulge of the galaxy. On the bright side, scientists have a chance of finding out more about dark matter and its interaction with other space objects by observing the behavior of the gas streams left in the galaxy's wake. Speaking about the formation of new stars, there is a galaxy with a name that speaks for itself: Baby Boom. Around 4,000 stars are born here every year, which is about 400 times more than in the Milky Way. Straightforward calculations show that on average, a new star lights up in this area of space every 2 hours. The Baby Boom galaxy lies around 12.2 billion light-years away from the Earth. This means that what we see when observing it is what was happening just 1.5 billion years after the hypothetical Big Bang. It was a time when the universe was still in the process of forming its structure. What is taking place in the galaxy now is drastically different from what we expect to observe there in theory, based on what we know about star formation. The reasons why stars are produced here at such an astounding rate are not known yet, but it is beyond any doubt that Baby Boom is able to provide us with a lot of information about the early stages of our universe's evolution. One of the few galaxies one can observe through an amateur telescope is the so-called Sombrero Galaxy, official designation M104. It lies 30 million light-years away from the Sun, and its diameter is roughly 4 times smaller than that of the Milky Way. The Sombrero Galaxy's outstanding feature is a massive ring of dust and cold hydrogen enveloping it. Observations show that it is here that most young stars are born. In addition to the peculiar ring, the Sombrero Galaxy is also remarkable for its elaborate inner makeup. Observations with the Spitzer Space Telescope show that most stars in this galaxy form a structure typical of elliptical galaxies. The stars here are mostly rather old yellow and red dwarfs. The other stars here, on the other hand, form spiral structures concealed within an elliptical cloud. It is thought that this phenomenon is a result of 2 galaxies' collision, with their stars subsequently and almost inevitably mingling together. It is incredible that the galactic structures survived a merge of that scale with minimal damage, are none the worse for this tremendous collision, and can still be observed. Another peculiar feature in the Sombrero Galaxy is exceptionally powerful X-ray radiation emanating from the center. It is assumed that the accretion disk of a supermassive black hole may be its source. The mass of the hole is estimated to be over 1 billion solar masses, which makes this enormous object one of the most massive black holes known to science today. There are also several sources of tremendously high frequency or terahertz radiation detected within the galaxy, although today their nature is still a mystery. Our galactic parade today is concluded with yet another object boasting an elaborate inner structure, the eerie M64 galaxy, rather aptly dubbed the Black Eye Galaxy. The nickname comes from a dark band of cosmic dust that partly conceals the galaxy's center from the observer on the Earth. Due to this line of cosmic dust, as well as the exceptionally bright active nucleus, it is impossible to estimate the Black Eye's number of stars even roughly. What we do know is that it is comparatively small and not so remote. Its radius measures 25,000 light-years, and it lies approximately 17 million light-years away from the Milky Way. The Black Eye Galaxy is made up of 2 well-defined parts. Interestingly, the inner disk with a bulge rotates in the direction opposite to that of the outer ring. The most likely explanation for such a bizarre makeup is that the galaxy formed after 2 smaller ones collided and merged in the distant past. Admittedly, it would take a combination of a number of mutually independent factors for such a fascinating and well-defined structure to form. For example, the progenitor galaxies would have moved at specific velocities and come together at a certain angle. The odds of a success would have been minuscule. In terms of the vastness of the cosmos, our planet is just a small rocky fragment traveling at incredible speed through boundless emptiness. For billions of years, it has been orbiting the Sun, maintaining a distance of about 150 million kilometers. However, the true size of our system is much larger. According to modern concepts, its outer boundary, which is considered the far edge of the hypothetical Oort cloud, is at a distance of about 100,000 astronomical units. Beyond this boundary begins the vast abyss of the interstellar vacuum, space so rarefied that there is on average only a single hydrogen atom per cubic centimeter. The distances between the nearest stars in our part of the galaxy are a matter of a few light-years, and a photon that has left the Sun can reach Proxima Centauri without ever colliding with a particle of matter. This vast void is a pervasive and integral part of the deep structure of the cosmos. It permeates the entire Milky Way, separating stars and planets, black holes and white dwarfs, super-dense pulsars and scattered nebulae. If you move outside the galaxy, you can see that it is surrounded by an even deeper vacuum. For example, between us and the Andromeda Galaxy lies 2.5 million light-years of exceptionally rarefied space. This distance is so great that 25 galaxies like ours could fit in it, yet it is filled only with the deepest cosmic vacuum. And this is only a small part of the great cosmic abyss. The Milky Way, the Andromeda Nebula and the Triangulum Galaxy, as well as about 100 of their satellites, are bound together by pervasive invisible threads of gravity. This structure is called the local group and is a large cluster of cosmic matter about 10 million light-years in diameter. The local group, in its turn, is part of an even larger formation, but a relatively small galactic filament by the standards of the universe, called the local sheet. This flattened structure, consisting of several hundred galaxies, has a diameter of about 46 million light-years, and its thickness is roughly 5 million light-years. The sheet is also part of an even larger association called the Virgo supercluster. However, very close to the local sheet, outer space suddenly changes its appearance. Here, the usual colorful universe is harassed by a giant black abyss known as the local void. In fact, the local sheet is one of its walls, the other conventional boundaries being the Perseus-Pisces supercluster and the Pavo-Indus supercluster. At the same time, the void is divided into conventional parts by several rarefied galactic filaments, and wide passages link it into a single network with the neighboring Sculptor and Hercules voids. Due to the cosmological expansion of the universe and the gravitational influence of the surrounding matter, the volume of the local void is slowly increasing. At present, its diameter is about 150 million light-years, and the distance to the center is at least 70 million light-years. Meanwhile, the nearest edge of this cosmic void is located very close to the Earth, at a distance of about 3.2 million light-years. Due to this proximity, the local void occupies a significant part of our planet's night sky, about 40%. The main plane of the Milky Way, containing many bright stars and large nebulae, covers the central part of this region from us. Still, its edges do remain accessible for observation. In 1854, a dwarf spiral galaxy was discovered a little north of the constellation Hercules. It was dubbed NGC 6503. Later, with the advancement of observation techniques, it became known that it is located in the middle of the local void, and its distinguishing feature is the incredible multicolor appearance. The spiral arms of the galaxy are permeated with bright red clots of heated hydrogen, and shining blue nebulae are stellar nurseries. The center is obscured by clouds of cool gas and dust, which have a noble brown color. NGC 6503 has a diameter of about 30,000 light-years, and its distance from Earth reaches 17 million light-years. Due to the gravitational pull of the Virgo supercluster, this galaxy is approaching us at a speed of about 43 kilometers per second. It is believed that its gradual approach to the local sheet will eventually saturate its space with interstellar hydrogen, causing an increase in star formation. It is estimated that in a few billion years' time, the current number of young stars could double, and the small galaxy will shine with renewed vigor. The motion of NGC 6503 is a clear demonstration of how the voids are likely to have come about. It is believed that the foundations of the large-scale structure of the universe were laid in the first minutes of its existence, at the time of chaotic mixing of matter and energy. Cosmic cataclysms of incredible power shook the young universe. forming local compactions and voids. Subsequently, clots of matter became proto-galactic clouds, and areas of space of reduced density became voids. Over time, the pervasive influence of gravity intensified this contrast, pulling stars and cosmic gas into relatively dense clusters, making the space and voids even more rarefied. Observations show that the vast majority of galaxies formed between 10 and 13 billion years ago. In addition, no significant differences have been found to exist between the age of galaxies located in voids and those that form global filaments. This fact also confirms the modern theory of the formation of the large-scale structure of the universe. Meanwhile, allowing for the cosmological expansion of space, we can assume that with time, the local void will become larger and more rarefied, and the Virgo supercluster will gradually disintegrate into several independent groups. At present, it is an association of about 30,000 galaxies concentrated in a region of space with a diameter of about 200 million light-years. At the same time, the total mass of the cluster is about 1.5 quadrillion solar masses, which is tantamount to about 1,000 galaxies such as the Milky Way. The Virgo supercluster is partially contiguous with two other galactic superclusters, the Centaurus and Pavo-Indus superclusters. At the same time, its other side borders on a vast region almost devoid of matter. It is called the Taurus void and is one of the largest known cosmic voids. It is rather difficult to study this part of outer space. The reason is that most of the void lies in the so-called zone of avoidance, a sector closed off from us by the Milky Way plane. The bright stars in our galaxy outshine the fainter and more distant sources, and interstellar matter absorbs and scatters their light. However, thanks to infrared studies, we do have some ideas about the structure of this void. The diameter of this tremendous void is about 200 million light-years, and the distance to the center is about 150 million light-years. When observing the void, one is immediately struck by the remarkably clear boundary between the relatively empty space and a bright cluster of galaxies located much further away. It is called the Perseus-Pisces supercluster and is one of the largest in this part of the universe. A transition this sharp is characteristic of dust clouds, even though infrared studies do not confirm their presence. In all probability, the clear boundary between the void and the supercluster is caused by gravitation, but the exact mechanism of their action still remains to be found out. Meanwhile, it is thought that the Taurus void, like most other cosmic voids, is not quite as empty as one might imagine. The way light passing through it is distorted suggests that this region may hide in its depths giant gas and dust clouds, the cradles of future galaxies. According to other hypotheses, huge masses of dark matter, the most mysterious substance in the universe, the properties of which are still not fully understood, may be contained inside the void. According to the most daring ideas, there are clots of antimatter or even more exotic matter with negative mass in the centers of cosmic voids. Nevertheless, despite their boldness, these hypotheses lie outside the boundaries of generally accepted scientific concepts, which makes it difficult to verify them experimentally. Currently, only 2 separate galaxies have been discovered tucked away in the space of the giant void. One of them, UGC 2627, has a spiral structure and resembles the Milky Way, while the second, known as UGC 2629, is an elliptical dwarf galaxy. Both objects are located almost in the heart of the void, at a distance of about 185 million light-years from us. The distance between them is small and is within a few 100,000 light-years. Perhaps there are other single galaxies hiding in the space there, but the Milky Way disk does not allow us to see them. Meanwhile, the Virgo supercluster, together with 4 other superclusters, forms a giant galactic filament called Laniakea. It contains more than 100,000 galaxies and stretches for more than 500 million light-years in space. Its gravitational center is the Great Attractor, a mysterious supercluster of galaxies located 250 million light-years from Earth. In its turn, Laniakea is part of a vast galactic stream, and further out, one can see that most of it is surrounded by a black abyss of unprecedented proportions. The light of distant galaxies is drowned in its emptiness, and even the mysterious and elusive neutrinos take billions of years to cross this cosmic abyss. To be honest, it is hard to believe that despite all the development of observational technology, such a gigantic void was noticed only 10 years ago. The year 2013. The University of Wisconsin-Madison. A team of astronomers led by Professor Amy Barger is working to determine the distance between galaxies. In the process, an unexpected and staggering fact is discovered. It turns out that Laniakea and most of its surrounding superclusters are enveloped by a cosmic void of unprecedented proportions. After making calculations, scientists discovered that its diameter exceeds that of any previously known void. The size of the discovered void turned out to be so enormous that several fundamental cosmological principles were questioned. It appears that the universe is much more elaborate than we imagined. The research done by Amy J. Barger, Ryan Keenan and Lennox Coey has led, in all likelihood, to one of the greatest astronomical discoveries of recent years. Their work has shown that our galaxy, along with its surroundings, is located in the middle of the largest supervoid known to science. It was named KBC, after the first letters of the discoverers' names. Observations show that the shape of the giant void is close to spherical, and its diameter may exceed 2 billion light-years. According to calculations, the Milky Way is located a few hundred million light-years from the conditional center of the Great Cosmic Abyss, and about the same distance from its edge. The discovery of a giant bubble of emptiness surrounding Laniakea helped to explain the paradox that had kept scientists busy for many years. The fact is that all galaxies in the universe are gradually floating apart due to cosmological expansion. Measuring the speed of this motion allows us to calculate the so-called Hubble constant, a fundamental physical constant characterizing the rate of expansion of space. However, if we take the galaxies closest to us to calculate the Hubble constant, it turns out that the rest of the universe is expanding too slowly. On the other hand, if we take distant objects as the basis, the Milky Way's surroundings are moving faster than they should. The discovery of the void has accounted for a lot. The fact is that the galaxies inside it, including the Milky Way and its neighbors, are constantly experiencing additional gravitational influence from objects outside the void. This creates an additional force that gradually stretches our cluster in different directions. It is also surprising that the KBC void is so huge that it comprises not only superclusters of galaxies, but also other voids. For example, the local void, as well as the torus void, are part of its structure. It turns out that compared to other voids, even though KBC looks large, it isn't quite so empty. Nevertheless, according to calculations, even this void is just a barely noticeable dark spot against the background of the observable part of the universe, the diameter of the latter reaching 92 billion light-years. If we look at the global map of the universe, we will see a lot of dark spots on it, close to the KBC void in terms of their size. Most of them easily fit within the framework of modern physical theories, while others show surprising and strange properties, difficult to explain from the point of view of science. and one of the most noticeable riddles of this kind in space is the Eridanus supervoid, also known as the CMB cold spot. It is estimated to have a diameter of 500 million to 1 billion light-years, and it lies at a distance of between 6 and 10 billion light-years from the Milky Way. This means that this formation is one of the most extensive elements of the large-scale structure of the universe. The void is located in the southern hemisphere of the Earth's sky and occupies an impressive area on it, several times larger than the full moon. However, it is impossible to see it with the naked eye. The CMB cold spot is visible only with the help of special telescopes that study the cosmos in the microwave spectrum. Thanks to these, astronomers have discovered that within the spot, relic CMB radiation of the universe is about 70 microkelvin colder than the metagalactic average. This deviation is nearly 4 times as intensive as the strongest anomaly previously recorded, and its gigantic size makes it a truly enigmatic object that requires extensive study. It is now believed that relic CMB radiation traveling through hundreds of millions of light-years of deep vacuum is gravitationally influenced by distant galactic superclusters. This causes the pervasive echo of the Big Bang to lose energy, making the CMB cold spot appear cooler in images than its surroundings. Nevertheless, this effect cannot fully explain the excessive cooling of relic radiation. According to calculations, the attraction of external galaxies can account for only a quarter of the observed deviation. It is assumed that the remaining 75% of the effect may be due to the impact of hypothetical dark matter or dark energy concentrated in the depths of the void. However, it is going to take a while before we can truly unravel this cosmic mystery. The history of the largest modern orbital telescope began back in 1996. Its development and modernization took as long as 25 years, after which the spacecraft left our planet and set out on its journey through space. It took James Webb a month to reach its destination point, located 1.5 million kilometers from our planet. Because the telescope is equipped with high-precision infrared sensors, it can see the dimmest and most distant space objects hidden in the depths of the universe. However, this unmatched sensitivity also has a downside. The intense radiation from the Earth, the Moon and the Sun interferes with the faint signals of distant stars and exoplanets. Therefore, in order to counteract this effect, the super-sensitive instruments were covered with a multi-layer heat-reflecting screen. The observatory itself had to be moved away from large celestial bodies and be located near the so-called second Lagrange point in the shadow of our planet. Still, the obtained results were absolutely worth all the effort, because James Webb helped us make quite a number of amazing discoveries pretty much from the very first days of its operation. With some of them quite expected, others, on the other hand, prompted additional questions. One of the studies with a paradoxical outcome was the spectral analysis of WASP-96b, a glowing exoplanet of extremely low density. It is located 0.045 astronomical units from its parent star and completes a full orbit around it in just 3.5 days. According to calculations, the mass of the celestial body is half the mass of Jupiter, and its diameter is 20% more than that of Jupiter. Because of the extreme proximity to the star, the temperature of the object's outer layers is quite high and reaches 1285 Kelvin, or just over 1000 degrees Celsius. Exoplanets of this type fall in the category of hot Jupiters and are distinguished by large losses of atmosphere due to stellar wind. Earlier measurements showed very clear lines of sodium in the atmosphere of WASP-96b, which was interpreted by the researchers as a sign of an unusually clean and cloudless atmosphere. The fact is that according to the available models of the structure of gas giants, this element can exist only in the planet's interior. As we can see traces of it, it means that the upper regions of the celestial body's atmosphere practically do not absorb light. It was assumed that thanks to this, the ultra-sensitive detectors of James Webb could look into the deepest layers of the exoplanet. However, the information obtained by the telescope turned out to be radically different. The outer layers of the gas giant contain great amounts of water vapor. It condenses in the upper atmosphere and can form a large haze or thick clouds, reflecting some of the light shed on it. Because of this, the temperature of the lower layers of the object may differ significantly from the calculated values. Perhaps the accuracy of the earlier study was insufficient, or else some of the data was misinterpreted. It is also possible that we do not yet know of a certain factor that would allow us to combine the results to form a single correct picture. WASP-96b remains a mystery, which means it still needs to be studied in more detail. Of course, James Webb's discoveries do not end there. For example, 69 light-years away, there is an unusual system consisting of 3 brown dwarfs at once. These cosmic bodies are too big to be planets and at the same time too small to launch a stable thermonuclear reaction in their interior. Brown dwarfs are usually difficult to detect, as the radiation of their surface is extremely low. But James Webb sees the universe primarily in infrared, which makes it easy to distinguish objects that are virtually invisible in the optical range. The 2 largest components of the system are very similar in their characteristics and are located quite close to each other. The distance between them is about 2 astronomical units, and their total mass is slightly more than 100 times that of Jupiter. The temperature of both objects is relatively high, reaching 2600 Kelvin or slightly over 2300 degrees Celsius. The third component of the system is at a much greater distance, about 100 astronomical units from the center. Its mass is between 14 and 23 Jupiter masses, and its radius is 20% more than that of Jupiter. Also, this brown dwarf is about twice as cold as its more massive companions. Observations reveal that the temperature of its outer layers is 1240 Kelvin or slightly below 1000 degrees Celsius. Nevertheless, the celestial body is considerably warmer than the gas giants in our system, especially given the absence of a star that would give it heat. It was surprising to find that the outer layers of this brown dwarf contain not only the usual components such as water, methane or carbon dioxide, but also minute particles of various silicon compounds. The simplest of these is quartz, but more complex substances have also been detected. These are thought to be concentrated in the atmosphere of the celestial body in the form of vast clouds. The existence of such clusters had previously been predicted from theoretical considerations, because silicon, being a product of stellar thermonuclear reactions, is quite widespread in the universe. Still, until recently, observations have not been able to confirm this hypothesis. It is thought that about 140 million years ago, there was a single gas dust cloud in the system's place, which later split into 3 independent clumps. This event may have been caused by the gravitational influence of a massive celestial body that passed close to the protostellar nebula. Remarkably, if the separation had not occurred, the total mass of the formed object would have been enough to start a self-sustaining thermonuclear reaction. In this case, instead of 3 brown dwarfs, we might have been observing a single tiny star. Incidentally, the James Webb equipment is capable of observing not only single objects tucked away in the depths of space, but tremendous space structures as well, that stretch for hundreds of light-years. One of them is the Carina Nebula, which is one of the largest stellar nurseries in our galaxy. This bright and vast cluster is located about 8,500 light-years from the Earth and has a mass of up to 900,000 suns. It contains not only giant clouds of interstellar gas and dust, but also thousands of stars, from the smallest ones to the most gigantic. This is where two of the Milky Way's brightest objects are located: Eta Carinae and WR25. The luminosity of each is several million times greater than that of the Sun. Unique objects like that certainly attract astronomers' attention. Besides, James Webb's infrared cameras are able to pick out great numbers of stars in the dusty haze, which were previously unknown to us. The point is that it is in this area in space that hundreds of young stars are constantly getting born. According to modern concepts, new stars are formed by gravitational forces that compress and heat up clouds of cosmic dust. During its evolutionary process, a protostar goes through several stages until finally a thermonuclear reaction kicks in its interior. This theory has been confirmed by multiple observations, but many details of this long and complex process currently remain understudied. The formation of a new star sometimes takes millions of years, but astronomers don't need that long to observe it. Thanks to James Webb's infrared sensors, thousands of protostars and young stars at various stages of evolution have been detected in the Carina Nebula. It is important to note that all these objects formed within the same gas cloud, which means that they are very similar in terms of composition and age. By observing them, researchers can fully trace the process of star formation and better understand what forces are involved. Some phases of this process, predicted only in theory, take hours or days, and with James Webb, the chance of capturing them is greatly enhanced. For all we know, we may soon be able to admire a photo of a young star flaring up thousands of light years from the Sun. Meanwhile, an 18-section mirror 6.5 meters in diameter and an onboard array of high-accuracy instruments allow James Webb to capture light from objects much further away, at the very edge of the visible universe. They are more than 13 billion years old, giving us a glimpse of the earliest times immediately after the hypothetical Big Bang. However, even James Webb would not have been able to see their luminescence but for one unique coincidence. The phenomenon of gravitational lensing has long been known to scientists. This physical phenomenon helps us to better see into the depths of the universe. And this is how it works. A powerful gravity generated by a massive body focuses and amplifies the light from a source behind it. Such an effect can be produced only on condition that a great many factors happily combine, so it is not surprising that it is one of the rarest phenomena in the universe. It is all the more surprising that while observing the galaxy cluster SMACS 0723, located about 4 billion light-years from the Earth, James Webb captured light of a space object passing through gravitational lenses as many as 3 times. In total, the radiation was amplified about 20 times, without which astronomers would hardly have been able to distinguish it from background noise. The object is thought to be a distant and very old galaxy, whose age is estimated to be 13 billion years. About 10 other star clusters have also been detected, which are thought to have originated between 200 and 700 million years after the genesis of the universe. According to some observations, they have a complex structure which takes tens of millions of years to form. This discovery will allow scientists to develop the existing ideas about the early stages of the universe's evolution and may even prompt to question its age. Unfortunately, we still know very little about such remote times, and James Webb will surely help us learn more about them. The Solar System is just one of the countless multitude of planetary systems scattered across our galaxy. As we know, it consists of a single star in its main sequence stage and 8 planets with their satellites. In addition, Our system contains over 1 million small celestial bodies like asteroids, comets, and meteoroids. The planet in the solar system lying furthest, at least that we know of, is Neptune. Its orbit's radius measures around 30 astronomical units, which is equivalent to approximately 4 light-hours. Amazingly, only a tiny portion of the solar system is encompassed by Neptune's orbit. The remotest object in the system discovered to date is the so-called Far Far Out, lying 132 astronomical units or 18 light-hours away from the Sun. Still, even this object, barely visible against a dark background of unfathomable space, is not at all close to the hypothetical Oort cloud, whose inner boundaries lie approximately 2,000 astronomical units away from the center of our system. According to some estimates, its outer boundaries stretch for up to 60,000 astronomical units at the very least, which is around 1 light-year. These limits are predefined by the Sun's gravitational influence, and what lies beyond is interstellar space. Moving further away, we will notice over 50 of all kinds of stars within 20 light-years from the Sun. These stars are really diverse, from dim and cold brown dwarfs to bright and widely known objects like Sirius, Procyon, and Altair. Some of them have their own planetary systems, with objects potentially capable of nursing and sustaining life. For example, the object known as Gliese 832c, which is 16.1 light-years away from the Sun, is similar to our Earth more than any other planet within the solar system that we know of. The average temperature on the exoplanet's surface reaches 253 Kelvin or 20 degrees Celsius below zero, and it takes the astronomical body just 36 Earth days to complete a full orbit around its parent star. In astronomical standards, the distance between us and Gliese 832c is relatively small. However, a space probe setting out from our system at a speed of roughly 17 km per second would take as much as 300,000 years to reach the exoplanet's environs. At our current level of technological advancement, it is impossible to design an interstellar spaceship capable of completing as long a journey as that. The solar system, together with its neighbor stars, is part of the Orion Arm. The latter, in its turn, is part of the Milky Way. It contains around 400 billion stars, and potentially over 1 trillion exoplanets of all sorts can be discovered there, according to estimates today. The main diameter of the Milky Way measures around 100,000 light-years, and the stellar halo may be twice as large. Even though the thickness of the main disk measures about 1,000 light-years, there is a clearly defined bulge in the galaxy's center. This bulge is roughly 3,000 light-years thick. The Milky Way is part of the so-called local group. This is a vast structure comprising over 50 galaxies concentrated within an area of space measuring around 10 million light-years in diameter. The Andromeda Galaxy, the Triangulum Galaxy, and the Milky Way are the largest of the lot. Some estimates show that the mass total of the cluster may reach as much as 3 trillion solar masses, with our galaxy and Andromeda accounting for the major part. With the distance from the Earth to Andromeda around 2.5 million light-years, it is considered to be our closest galaxy, not counting smaller or dwarf ones. Moving on to the next order, the local group forms part of the giant Virgo supercluster made up of over 30,000 galaxies. The supercluster is located within an area of space with a diameter of around 150 million light-years. Its mass total is as much as 1 quadrillion solar masses, or in other words, around 1,000 galaxies like the Milky Way. The supercluster is quite flattened, and around 60% of all the objects it is made up of appear like a flat sheet around 10 million light-years thick. Staggering though it may appear on the face of it, this value is actually small in terms of the large-scale structure of the universe. As we zoom out still more, we have a chance of seeing a giant supercluster of galaxies approximately 520 million light-years in size. Called Laniakea, it includes several galaxy superclusters, among others the Virgo supercluster and the Great Attractor. The overall mass of this formation measures approximately as much as 100 quadrillion solar masses. The Great Attractor lies roughly 250 million light-years away from our planet and is the gravitational center for all objects lying close by astronomical standards. It cannot be observed from the Earth directly, as the Milky Way's plane thwarts it. That is why the nature of the Great Attractor still remains an unsolved mystery today. Laniakea is part of the large-scale structure of the universe, an elaborate system of galactic filaments, walls and voids, gargantuan areas of emptiness in space. Some of these objects are really incredibly enormous. For example, the Hercules Corona Borealis Great Wall stretches for around a staggering 10 billion light-years. Ever since its discovery in 2013, this superstructure has been considered the most gigantic component of the large-scale structure of the universe. To all appearances, it must be home to millions of galaxies, and the number of stars it contains will probably always defy calculation. The mere existence of a structure like that is a mystery to science, as according to today's accepted theory of universe's evolution, gargantuan clusters like that are simply not supposed to form. But incidentally, this wall, so enormous that the human brain cannot fully appreciate its dimensions, is still just a tiny portion of the observable universe. According to today's cosmological notions, space in the universe is continually expanding, with the speed of expansion depending on the distance between objects. The further an observed object lies away from the observer, the faster the distance between the two increases. The rate at which the two mutually recede is not limited by the speed of light, because it's actually space matter that is expanding, which means that at a certain point the two objects will be mutually unobservable. Relic radiation observation shows that the area of the observable universe is a sphere, with a diameter roughly 93 billion light-years. According to the theory of relativity, we can see and interact with only those objects that are within this sphere. This conventional spherical area in space is called the meta-galaxy, and it may be either all of the universe, or again its tiny portion. For all we know, hypothetically, there may well lie some unknown structures beyond the visible boundaries of space. Such entities are referred to as extra-metagalactic objects, and unfortunately it is impossible to study them today with scientific methods. Still, some astronomical bodies on the edge of the visible universe appear to be moving in ways different from what we would naturally expect, judging by the data we have. Instances of anomalous movements like those may be evidence of the presence of some massive structures beyond the meta-galaxy boundaries. Their attraction pervades the space around and influences objects around too. There is a whole plethora of hypotheses as to the structure of the universe beyond the meta-galaxy, but most of them are rather of metaphysical nature. For example, some people believe that time and space, as we more or less know them, are non-existent beyond the boundaries of the universe. The physical laws we're used to do not apply there either, and notions of matter, material, or energy are virtually senseless. This hypothesis is further elaborated on by the following idea. The meta-galaxy accounts for just a part of a yet more complex and larger-scale superstructure in space whose makeup and dimensions are too incredible for us to imagine. It is quite possible that this structure could be in a multidimensional space, or else be based on physical principles we have no idea of. This makes the meta-galaxy just an insignificant addition to or a partial reflection of this mind-boggling superstructure. According to some interpretations of the anthropic principle, there are other worlds out there beyond the boundaries of the observable universe. In those worlds, the values of the fundamental constants like the speed of light or the electron charge are completely different. This hypothesis is in many ways supported by the idea of a multiverse, which schematically appears as foam with lots of bubbles separated from each other by thin walls, but these walls are impenetrable. This makes every universe a separate space, with its own physical laws, and for all we know, these laws may be totally different from the ones we're used to. The most radical hypotheses go as far as to deny our world any objective reality whatsoever. According to these, the universe is just a simulation like virtual reality in computers, but on an incredibly advanced level. As a rule, ideas like that imply that there are some super beings or super civilizations out there beyond the reality we're used to, whose level of advancement is infinitely higher than ours and whose goals and capabilities are arcane and incomprehensible. However, it goes without saying that it is hardly possible to either confirm or repudiate these hypotheses. The solar system is a barely noticeable speck against the vast universe, and the entire history of our civilization is just a brief instant by space standards. While a single photon crosses the vast expanses of the Great Void, whole epochs pass on our planet, and the Earth's appearance changes beyond recognition. This scale is barely comprehensible to our minds, and the greatness of the universe never fails to amaze and make one wonder. And it goes without saying that there are many more outstanding space discoveries ahead of us. And let's keep in touch.